What are the challenges of using extreme scale computing for machine learning? That's one of the questions that my guest today is going to explore at an upcoming workshop at SC21 in St. Louis. Robert Patton, will you introduce yourself and the institution that you represent?
Sure. I'm Robert Patton. I am the group lead for the Learning Systems Group at Oak Ridge National Lab. And we focus, a lot of our research is on artificial intelligence and applying that in extreme computing environments such as supercomputers.
So tell us a little bit about what this workshop on machine learning, what kinds of things are you going to be exploring there?
Yeah. So the workshop was started, the first year of it was in 2015, and the intention of the workshop is really to get a community of the research community together to look at what happens when you take artificial intelligence algorithms or machine learning algorithms to an extreme in terms of what sort of data and what sort of compute power do they need. What happens when you take AI from a desktop computer running on maybe small scale hardware or small data sets, and what happens when you just push the bounds on what's possible, and where does stuff work, where does stuff break, and if stuff breaks, then what are the algorithm enhancements that people have done to say, hey, this works, I just did this, I couldn't do it before, but here's our approach and now it works, and publish, talk about those results. So that's really what we try to focus on.
Can you give us some of a preview of maybe what some of those applications or those extreme cases might actually be?
Yeah. So right now there's the training process for a lot of the neural networks that are out there is a very compute intensive process. And many years ago, a lot of the neural networks made a jump from CPUs to GPUs, graphics processor units. And they really benefited from all that compute power. And so, kind of begged the question, if one GPU was good, well, what do you do when you got 20,000 of them, right? Then what do you do? And that's where you start looking at the algorithms to go, okay, the algorithms may not leverage all that hardware very well. How do they communicate? Those sorts of things. And so, there's a lot of application. This is one of the things that's interesting about artificial intelligence, is that to really push the fundamentals of artificial intelligence forward, you have to have the applications that drive it, right? And it's this sort of back and forth between, I want to apply AI to this application, but it doesn't quite work. So I need to come back to the AI to go, what do I got to do to make it work? And you try it again, that sort of thing. So right now, we're just kind of in this realm of AI plus application space, and you fill in the blank. And it's applications that are all over the place, all around the world. And right now, this workshop in particular, we try to focus on scientific applications. How can AI be applied to biology or nuclear physics or some area of science where we say, hey, if we can bring AI to bear on this problem, it may enable new scientific discoveries that weren't previously possible, right? And so those are the types of things that we look at then and say, okay, given this application space, how does AI work or not work? And do we need better data? Do we need better simulations? Do we need better algorithms? Do we need more compute? What works and what doesn't work, right?
And it sounds like the answer to a lot of those questions is a definite yes. We do need more, right?
Yes, yes, exactly. More of everything.
So one of the areas that is mentioned in your outline for this workshop is exploiting data parallelism. Can you put that into plain English for our viewers?
Yeah. So there's two approaches to scaling AI algorithms. There's a data parallel and there's a model parallel. Model parallel is a lot more difficult, where you're trying to take the neural network and stretch the single neural network and stretch it out across multiple compute devices. Data parallel is where you kind of stretch your data across compute devices, and you have your neural network trying to learn across those different compute devices from your data. And so that's really what we look. That's the little bit easier approach to do, because data can oftentimes be parallelized a little smoother. So those are some of the things that have made more progress, is the data parallel approaches. But there's limits, right? I mean, the data sets, you may have heard in the media recently about biases of AI, how AI may be biased against
Right.
people and stuff like that. And it's not that there might be a misconception there that somehow AI is coming out as being racist or biased or something like that. And it's not that the algorithm is biased, it's that the training data, the data sets, have a bias in them, whether that's intentional or not. And what do you do about that, right? And when you start pushing things to an extreme, well, then any sorts of problems you have with your data set are going to get amplified, right? And what do you do about that? Do you go get more data? Maybe it's not possible to get more data. Maybe you have to get synthetic data to supplement. Maybe you've got to go to a simulation, right? So those are the things that we try to address, those topics in the workshop.
So I'm thinking in terms of analogies, and if you just have regular, ordinary humans and they get married, marriage is complicated, right? But is this a little bit like when we get into the old science fiction realm, where you have a Frankenstein that you don't know what he's going to do, and you have a bride of Frankenstein and you don't know what she's going to do, and you marry those two? Then there are all kinds of possibilities you probably wouldn't regularly explore, because there's that multiplier effect of the unknown, right?
Yeah, sometimes we call that the emergent behavior. But yeah, exactly right. I mean, that's one of the things that is always surprising to me, and is that with artificial intelligence, with some of the things that we're doing, we have created algorithms that are capable of doing things that are quite amazing, and in some cases are beyond what even humans might be able to do. And yet we still don't fully understand how is it that those algorithms are working, right? How is it that they're performing so well? I mean, there's mathematics behind it. We know what the mathematics are, but then it's like, why does that work? And if we make a change, there's not a good theory to say here's exactly what's going to happen, right? There's a bit of an unknown there. And so that's exactly right, where you take some neural network algorithm that you're not quite sure what's going to do, you put it on a supercomputer, and you max out the data, you max out the compute, and go, this is going to be interesting.
Very good. So for attendees, people who are looking at the outline of this online and watching this interview and thinking, I might be interested in attending this workshop, what kinds of tempting things can you talk about that might help them make the decision, oh, I definitely want to do this?
Yeah. So what we've done in the past, and which is what we'll continue to do here, is we try to invite some one or two keynote speakers who can come and bring a very big perspective on a topic that a wide range of people are going to be very interested to hear. And then we're going to have a series of presentations that are going to dive into some of the weeds, to go, here's an application, or here's an algorithm, and they're going to explain, here's how it's working, why it's working, what happened to it. And there's a fair chance that those applications are going to be something that the audience is going to be very interested to hear.
Excellent. Well, we'd like to conclude this time together with you, this interview, with you giving a plug to your laboratory and the work that takes place there. Feel free to give us an unabashed plug.
Great. So, Oak Ridge National Lab is actually the largest open science laboratory that is operated by the Department of Energy. We have a wide range of applications and science areas all over the place. I think the only potential science that we don't really do a whole lot is high energy physics. Everything else, there's someone there trying to do science in all sorts of different ways. And what's fascinating, what's fun is that we're trying to apply AI to those areas, right? And how does AI help us push the bounds in those science areas? And then, of course, we operate one of the fastest supercomputers in the world. And so you'll often see us trying to say, how is that machine leveraged for those science applications? And so those are some of the things that we try to go after and accomplish.
And talk to us about what your role is with the lab.
So my role is I'm a group lead. I lead a group of research staff whose expertise is in artificial intelligence. And we actually run on the supercomputer. We work with domain scientists to do everything that I described there, where we try to partner with other domain scientists who come and say, hey, I'm trying to apply AI to this area of science. Here's the problem I'm trying to here's the problem I'm trying to address. If AI can help me in this, let's do it. How do I do that, right? And so that's where people from my group will work with them to say, okay, let's figure this out. What is the problem? What does the data sets look like? What does the problem look like? You know, how are neural networks applied to this domain, and what's the right way to train them, and so on. So that's a lot of the work that I do.
Wow, sounds very exciting. What kind of education was needed for you to be able to ascend to this role?
So I have a PhD in computer engineering, and a lot of that is in how do you make intelligent algorithms better, faster for different hardware, right? And so that's where, you know, naturally led into exactly some of the things that we talked about. Is there's a lot of computer science algorithms that may run well, but then you have to marry it with the hardware to say, how can we make it run better? Right. And so that's where a lot of my background is in.
So I have been doing some reading lately about the human brain and how the author that I was reading was making the case that of anything that we know about in the known universe, the human brain is the most complicated and most mysterious of all mechanisms. And I think he was making the case that there are more known dendrites and neurons going on in the human brain than there are planets in the known universe. I guess my question is, as we get closer, as we explore these extremes of extreme machine learning and artificial intelligence, have we surpassed that, or is the brain still the greatest mystery?
I firmly believe that the brain is the greatest mystery, and that we are not even close to touching what the human brain is capable of. You know, one thing, and I can understand. I mean, I'm huge into science fiction, of course, and I love the sci-fi and all those sorts of things. I'm all about the droids and stuff like that. But I can see how people might see the results of today's AI and go, wow, this machines are really smart. One thing to keep in mind is that when you see that, you need to recognize that neural network has been trained to do just that task and nothing else. That's all it knows to do, right? The human brain, we can do so many different things, and sometimes even at the same time, right? And so there's just so many different things right now that current artificial intelligence, you know, it might be able to surpass a human being able to do facial recognition, but that one algorithm, that's all it can do.
Yeah.
That's all it can do.
Well, and I'm thinking about these, I think I saw something on 60 Minutes, a repeat of the amazing things that are going on with robotics. Mm-hmm. But we can be out walking or running and see someone and recognize them. And then there's all this other stuff that the brain's doing, right, that we're not conscious of, that allows the balance and the running, and let alone the breathing and the heart rate and all that kind of stuff.
and doing all of that with very low energy consumption, right? That's the other thing too. I mean, the amount of electrical power we need to run some of these devices far exceeds the human brain, right? So that's the other thing too, is like our human brain is exceptionally powerful, but it's also very energy efficient, right? And so that combination is something we haven't even come close to yet.
I wish we could just keep on talking, Dr. Patton. This is fascinating stuff, but it's a good preview of why people should come to your workshop.
Well, thank you. I appreciate the opportunity to share about the work that we're doing, and I look forward to seeing so many faces in the audience, and I hope they enjoy the content.
Thank you for being with us today. And to our viewers, join us again soon for another edition of SC21 TV.